Example 188, use the Wilcoxon signed rank test to test the claim at the 5% significance level that there is no difference between the yields from regular and kiln-dried seed. So they have the yield of corn for different seeds. They probably, they're telling us that to use the Wilcoxon signed rank test, which means this is a paired difference experiment or a dependent scenario. So probably what they did is they probably took the seeds here from the same source, and half of them they probably dried the regular way and half of them in the kiln they dried. And this way they would be able to, make the comparison, assuming that the seed itself was basically the same. And they would do the same for this column of data, this column of data, this column of data, so on and so forth. All right, so what we want to do first is express the claim, and let's do that in the initial step. The claim here is about a pair of medians initially, so you could say, for example, if there's no difference between the two, that the median for the regular method is equal to the median for the kiln-dried method. So that would be essentially what you're supposed to do for that part. And then for the HO-HA, you would do a similar thing, right? HO-HA. So we would have, for example, here the median for the regular method is equal to the median for the kiln-dried method, and then the median for the regular method is not equal to the median for the kiln-dried technique, right? So again, equal pairs up with not equal to, as it did before. You could also kick this value over and then talk about the median difference. So in other words, if you move this value over, you end up with this, right? So the two medians subtracted equals to 0, and then you could further extend that out to say that this means what? The median difference, calling this a difference, is equal to 0. So using the same analogous approach, we could also say the median difference is not equal to 0. So that's another alternative way to express the HO and HA. I'll leave it up to you, whatever you decide to use, or look at what your professor uses and use that technique, because they're equivalent. So claim HO-HA, that's taken care of. Now we would normally manipulate the data. To manipulate the data here, we actually have to fill in a bunch of information beneath the problem here. So I'm going to go ahead and do it right there beneath the problem. We're going to actually subtract each of these values one by one. So we're going to get the differences first. Once we have the differences, we're going to then take the absolute value of the differences, and then we're going to rank those differences. We're also going to discard any ties that we have. So first I'm going to do the differences. So I'm going to create a column here of differences and just start doing that in the calculator. Okay, so I'm going to do 1903 minus 2009. And when I do that, I get negative 106. So minus 106. I'm going to do this again for the next category. So 1935 minus 1915, right? So I'll get the 20 there as a positive 20, and I'll just fill that in, right? So 1910 minus 2011. And when I do that, I get negative 101 minus 101. Continuing, subtract these two, you'll see that I get a 0. 0 differences have to be discarded, so we'll remember that for later, right? We don't want to consider 0 differences. We throw out any ties that occur. So 2108 minus 2180 ends up giving us negative 72. Then 1963 minus 1925, and we get the answer 38. 2060 minus 2122, negative 62. 1444 minus 1482, we end up with negative 38. 1612 minus 1542, we get 70, positive 70. 1316 minus 1443, we get negative 127. And then lastly, 1511 minus 1535. Okay, so negative 24. Okay, so I wanted to do all these subtractions with us here together. That way you would feel comfortable seeing how we create the different columns or rows that we need. So we have the row here for differences. Now, from there, we're just going to take the absolute difference, right? So in other words, we're literally going to say, okay, what's the absolute value of these differences that I just came up with? So that would be 106, right? 2101, I'm going to cross this out. I'm going to put an X there because we do not want to use 0, right? 0 is not going to be part of our look here. We're going to ignore any difference that's 0. Then I'm going to look at this value here, call it 72, then 38, then 62, then 38, then 70, then 127, then 24. Now that I have those, I want to rank those differences. So the next step is to do the ranking. So to do the ranking, I'm going to look at the list now, initially, as if essentially, it's all one set of data, right? And I'm going to rank those values from 1 being the smallest all the way up to the highest, right? So what's the smallest number we see here? I think 20 is the smallest number, so I'm going to give that rank 1. What else is in here that's small? Well, we've got 24. That should be rank 2, perhaps, right? Then it looks like we have something in the 30s, the 38s. So I would give this 3 and 4 provisionally, but I'll circle those because I know those are tied, right? And then I continue on. So looking for anything else higher than the 30s. Well, I have 60 is, I think, the next highest, so I'll give that rank 5. And then I have something in the 70s, so I'll give that rank 6, and then this rank 7. And then I have 101, I think would get rank 8. And then this will be rank 9, and then lastly 127 gets rank 10. And this, remember, is discarded, so I'm going to cross that out again just to make sure that that's not used. Now remember, these are provisionally 3 and 4, but I'm going to change them now to 3.5 each, the average of 3 plus 4 divided by 2, which is 3.5. So I'm going to change those two to 3.5. Now I have a ranking for every value. And from there, what we're going to do is we're simply going to come up with our test stat based on the rank totals. So before I move on to the test stat, I just want to summarize what we have here, and I want to say, okay, which one of these ranks belong to negative numbers initially? I'm going to kind of put a little square around the negative ranks, right? Everything that involved a negative value initially. And when I do that, I see that there are quite a few of these ranks that involve negative numbers initially, right? In other words, these guys here are all negative values. So if I want to add up the negative ranks, I can do that, right? I can say, hey, look, the rank total, we'll call this T negative for the rank total for the negative ranks. That's 9 plus 8 plus 7 plus 5 plus 10 plus 2. So let's do that and add that up and see what we come up with here. Actually, I think I left one of those out. So anyways, it's 9 plus 8 plus 7 plus 5 plus 3.5, right? Plus 10 plus 2. All right, if you add all together, you get 44.5 for that value. 44.5. And if you want to do T positive, then that's just the leftover ranks that are positive. That's only going to be 1, 3.5, and 6. So I'm going to get 10.5 for that one. 10.5. Again, the rank totals, the sum here has to add up to the total number of ranks I would have given out. How many ranks did I have? Well, I ranked 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. So I should have 10 times 11 divided by 2, or a total of 55, right? 10 times 11 divided by 2. That'll give me 55, and the sum of this indeed is 55, and that's what it's supposed to be. So it looks like those rank totals are correct. All right, so let's look at our test stat next. Okay, so now let's define our test stat. Our test stat is going to be T, which is going to be equal to the minimum of the two values we just calculated, T negative and T positive. So what we mean by the minimum, we mean the smaller of the two numbers. So in our case, it's going to be what? 10.5, right? Because of these two numbers that we calculated, 10.5 is the smallest. So that's our test stat for the problem. Now, once we know that test statistic, we're going to want to compare it against a critical value. So we need to get critical value from the table. Since we're taking the minimum of the two numbers below, the logic of this test stat is very simple. If it's very small, smaller than the critical value, we'll reject the null hypothesis. Because if it's very small, it shows that there's a significant difference between the two rank totals, and that would mean that essentially one has a much larger yield in this case than another. Okay, so let's do that then. Let's go to our critical value, and we have to go there armed with certain information. We need to know for the critical value the following things. We need to know what alpha is. So what's alpha in this problem? It's 5%, right? So 0.05. We need to know what kind of test is it, one-tailed or two-tailed. that's a two-tailed test, right? So 2 tails. And then finally, what you're going to need to know is you're going to need to know ultimately how many different values you had. In other words, how many pairs you had after you discarded the ties. So how many pairs did we have? In other words, what was our n? Well, if we look at it, we had 1, 2, 3. We threw that one out. 4, 5, 6, 7, 8, 9, 10. So n is 10 for us. Okay, let's go to the table now and find, using these values, our critical value. Okay, so we're at the sign rank test table, and we're looking for 0.05 and 2 tails here. So in the 2-tail column, 0.05, and we have n being 10, we find the answer 8. So our critical value, T0, is 8. Okay, so our critical value from the table, which we'll call T0, turned out to be 8. Now the rule is very simple. If T, our test stat, is less than or equal to T0, we're going to reject HO. If T, our test stat, is greater than T0, then we're going to say do not reject HO. And you know the corresponding things that go with that. Rejecting HO means you support HA, and do not reject HO means you do not support HA. So what's our scenario here? Well, our T is 10.5. Our T0 is 8, so we have a greater than symbol between these. So we're going to say do not reject and do not support HA, right? So do not reject HO, do not support HA. That becomes our pair of conclusions. Since our claim is HO, we will actually say that we cannot reject the claim. So the sample data does not allow us to reject the claim. I don't want to beat a dead horse here, but I do want to reiterate again that non-parametric procedures are weaker than their parametric counterparts. So in other words, the dependent t-test or matched paired t-test is stronger than or more powerful than this Wilcoxon sign ring test. And as a result, it might be possible that if we used that t-test procedure instead of this non-parametric procedure, that we might have been able to reject the null hypothesis. After all, there was a pretty big difference between the rank totals for the two scenarios. So it could be that maybe we weren't able to reject here because the test is not as powerful as the dependent t-test would be. So that's always an issue when you cannot reject HO. So when you can't reject HO, you have to wonder, maybe I didn't reject this because my test just isn't powerful enough to detect a false null hypothesis here. But in either case, according to what we had in this problem, a 5% significance level, a two-tailed test, n being 10, and using the Wilcoxon sign ring test, our conclusion is that we cannot reject the claim, and this means we cannot say there's a difference between the yields from regular dried seed and kiln dried seed.